Should stop sharing?
Yes. Okay. So maybe we can start, right? So yeah, it's great to see you all here. This is this lecture series that we nicknamed Summer Camp on Boolean Functions. It's sort of meant to highlight the recent exciting advancement in the area that happened over the past few years. It's really remarkable to see all these long-standing conjectures being, resolved one after the other. And we have a great lineup. So today will be the first talk. The schedule has been changed a bit over the last few days because of some conflicts that we had with CCC. So this is the updated schedule. I hope that it will not change after that. So the first talk is today by Dor. Next week, we would have How talking about the sensitivity conjecture. And then we'll have a break of 1 week because of CCC. And then the following week, we'll have 2 lectures, one by Shachar Lovet on improved rounds on the sunflower lemma, and another by Ronen and Dan, using stochastic calculus to resolve open questions in Boolean function analysis. The week after that, we're going to have Esti Kelman about a new proof for the KKL inequality via random restriction. And then we'll have Puya Khatami talking about pseudorandom generators from random walks. This is the plan currently. The reason we stopped is that the semester in Simons starts immediately after August 18th. So we didn't want to clash with that. It might be the case that we would add some lectures after that, but this is the current plan. Okay, so anyway, the website now is updated, and you can see the list, and you will see abstract of every talk. So maybe we should start with today's talk. Prasad, do you have anything to add before we start with the talk?
Oh, no, I think that was good. Yeah, maybe. Yeah.
All right. Okay, so we are very happy to have Dor Minzer speaking today. Dor has done remarkable work on several areas. Is very well known for his work on the unique games conjecture, and he proved the 2-to-2 conjecture. Also had remarkable contributions to probability testing, monotonicity testing, and recently resolving on making progress on some of the biggest open questions in analysis of Boolean functions. He finished his PhD in just 2 years in Tel Aviv University. In the last 2 years, he has been in the Institute for Advanced Study in Princeton, and is going to start a position at MIT soon. And I think he will be in the fall in the Simons Institute, or at least in some way or fashion. So we're very happy to hear Dor talking about the Fourier-Entropy conjecture. So Dor, the floor is all yours.
Thank you very much, Avishai. Thank you all for coming to this talk. So I'm going to talk about some new results about the Fourier-Entropy conjecture. So this is joint work with Esti Kelman, Guy Kindler, Noam Lifshitz, and Muni Safra. So let's go. So before I even tell you what the Fourier-Entropy conjecture, let's set up some basics. So this talk is intended for, at least this part of the talk is intended for general audience. So please feel free to interrupt me at any point if you have any questions.
Maybe we should let them know that the questions they can type out on the stream, and we'll forward it to you.
Okay. Yeah. So here are 2 things that are going to be the same for this talk. So for this talk, we'll always consider the Boolean hypercube equipped with the uniform measure, and for us Boolean will be ±1. It's more convenient, and we'll study Boolean functions f from -1 to the n to -1. And for simplicity, this talk will only consider balanced functions, meaning functions that get the value 1 and -1 equally likely. Of course, all of what I'm going to say can be generalized beyond this case, but this is enough for today. And we start with a very basic definition, the definition of influences. Good. So what is the influence of the ith coordinate on a function f? Well, the influence of coordinate I on f is the probability that when I look at a point x chosen at random, and at a point x plus ei, which is the same point as x, except that it's different on the ith coordinate, then the influence of I is the probability that I get two different values in the function f. So these are influences. And once you define these probabilities, you can certainly sum them up. And this is called the total influence of the function f. So at this point, it's not really clear why does it make sense to sum this up. But this total influence also goes by several other names, such as average degree and average sensitivity. We'll see why for at least one of them, but this is a really key parameter of a function. And sort of one of the key questions in the area is the following. Suppose I have a Boolean function, and I'm promised that this function has small total influence. Say total influence is at most k. What can you say about its structure? And for this question, you can think of k as coming from several different regimes. So the first regime is where k is some constant, say 100. But it also makes sense to look at this question when k is even log n, say 10 log n or something like that. And I'm not going to elaborate on that, but this question does not appear out of thin air. It appears in several places. So for example, it appears in TCS. For example, in PCP, it appears in learning theory, external combinatorics, and in sharp thresholds. So this is certainly a question worth studying. Good. So the first regime in which this question is interesting, and also kind of the easiest question in quotation mark, is when you think of k as a constant. And in this case, we really have satisfactory answer to this question, and these answers go by the name of the KKL theorem and the Friedgut theorem. But before we say the theorems, let's consider a few examples for functions that satisfy this property to get the hang of what we can expect from. So here are two examples. So how can you arrange for the total influence of a function to be smaller? Well, your function can depend only on one coordinate. Let's say your function is a dictatorship. The output of it is simply the first coordinate of x. Then it's easy to see that all the variables except the first one have 0 influence, and the total influence is 1. Okay, but in general, you can consider any function that depends only on k of its coordinates. So these are functions that are known as juntas, and this will also satisfy this property. So these are the two examples, and what the KKL theorem and the Friedgut theorem say, very roughly speaking, is that these are the only examples. So let's be a bit more precise. So here is the KKL theorem. So this theorem says that if you have a function whose total influence is smaller, then at least in some sense, it resembles a dictatorship. In the sense that there exists a variable whose influence is fairly significant. And when I say significant, I mean like e to the minus k. So remember, here we think of k as like 100. So e to the minus k is a lot. So this is a great theorem, really, and actually we'll see a proof for this theorem later in these slides. But it doesn't give you really satisfactory answer because it's kind of a weak structure. You can hope to say more. And indeed, you can say more. And this is exactly the Friedgut theorem. So this theorem says that if you have a function with small data influence, then not only is there a variable with high individual influence, but in fact, your function essentially only depends on these variables. And sort of as a straightforward corollary, you get to say that f essentially depends only on e to the k many coordinates. And we say essentially this is a bit informal. The formal statement is written on the slide, but don't worry about it too much. What you should have in mind is that f really depends on very few coordinates. Good, so these are really two great theorems, but and they're great for as long as k is small, but that's it. So once you pass this log n, this k equals log n, both of these theorems become completely meaningless. Like if k is log n, e to the k is more than n. But the input of the function is at most n variable, so what are we even saying here? Not much. And this is really a well-known barrier in analysis of Boolean functions that people sometimes call the logarithmic barrier, because we know to say many things about functions with total influences significantly smaller than log n, but essentially nothing when we pass this log n barrier. Good, so with this opening, now I'm going to tell you what we're going to see in this talk. So first of all, I'm going to have to tell you a little more of basics of Fourier analysis. I'll try to do it step by step. Just enough so that we can state the Fourier-Entropy conjecture, and then tell you what are the main results that we prove in this work. Then I'm going to tell you about a very useful tool, like the main engine that goes behind all of these theorems, which is called the hypercontractive inequality. Then I'm going to show you a proof of the KKL theorem. It's going to be useful for us. And finally, I'm going to tell you about the proofs of our results. And the way it will work is that the first hour of this talk will be dedicated to more of the standard stuff of stating the results and telling you the proof of the KKL theorem, which will be useful for us. And in the second hour, we'll have more fun in the sense that we'll start proving things, and I'll show you how you can get some new bounds for Fourier-Entropies. Yeah, so let's go. Okay, so what is Fourier analysis? So the starting point of Fourier analysis is to look at all really valued functions over the cube and to think of the set as a vector space. So this is a thing we've all done in linear algebra over some domain or another. And what is nice then is to define an inner product. So this gives you lots of tools. And indeed, we define an inner product. So the inner product between two functions is the expectation inner product. So the inner product between f and g is the expected value of f of x, g of x. And later on in the talk, I'm going to use some norms. And whenever I use a norm or an inner product, it's always an expectation. Good. So the next basic thing about Fourier analysis is to choose a basis. And with the plus-minus one notations, there is a very natural basis to consider, simply the basis of monomials. So for each subset of coordinates s, we define a function chi-s from the cube to -1, 1, which is simply the product of xi when I is in the set. And a very standard fact, which is easy to prove, is that if you look at this collection of functions, then this is an orthonormal basis for the vector space of real-valued functions. Of course, with respect to the inner product we just defined. And so what do we know? So we know that once we have an orthonormal basis, we can decompose any function according to this basis. And this is, in this case, called the Fourier decomposition. So we can write any real-valued function on the cube as a linear combination of this character. So this is this representation of f of x as summation over s, f hat s, chi s. And because this basis is so nice and it's orthonormal, you get for free a very nice formula for the coefficients of this decomposition, which are simply the inner product between f and the corresponding monomial. Good, so let's do a little more basics. So here is a fact. We have what is called the Parseval or Plancherel equalities. And by this, I mean that if you have two functions and you want to compute the inner product between them, then this is the same as the inner product between the Fourier transforms up to normalization. So by that, I mean that instead of explication of a character, you take sum. So I hope that you've all seen a variant of this equality in one domain or another. And when the function f and g are the same, this is usually called the Parseval equality. And a particular case of interest for us will be when f is equal to g is a Boolean function. Again, by that we mean that it is plus minus 1 valued. And in this case, we get that the inner product within f and itself is on the one hand 1, and on the other hand, it's summation of the squares of the Fourier coefficients of f. So why am I stressing that? Well, we have a bunch of non-negative numbers which sum up to 1. We have a name for these collections. These are distributions. So it will be useful for us to think of this as a distribution. So let's say it again, the squares of the Fourier coefficients are a distribution over characters. So in particular, you can ask about the properties of them as a distribution, such as entropies and other things. And indeed, this is the parameters that the Fourier conjecture address. Good, so now that we have enough basics, we can state the Fourier-Entropy conjecture of Friedgut and Kalai. But let's start with a moral statement. So the moral statement says that if you have a function, again a Boolean function, that has small total influence, at most k, then its Fourier spectrum is sparse, in the sense that almost all of the mass of f is concentrated on e to the k many coefficients. So this is the moral statement, and if you don't want to think about like complicated formulas, I suggest that this is what you have in mind. But if you want to know what the conjecture really states, then this is the following statement. It says that there exists an absolute constant c greater than 0, such that for any Boolean function, if you look at the Shannon entropy of f at squared, then this is at most the total influence of f times this absolute constant. And by Shannon entropy, I mean the usual Shannon entropy, which is summation of f at squared log of 1 over f at squared. If you've never seen Shannon entropy, I encourage you to think about it as like log the size of the support of the distribution. Of course, it's not the same, but for the purposes of this talk, it's enough. Yeah, so this is the Friedgut-Kalai conjecture. So why study this conjecture? Well, so this is kind of the first non-trivial structural result you can ask about functions with total influence 10 log n. or something like that. So even coming up with statements regarding this function is hard. And this is one very nice statement in my opinion. And the message here is, it's clear. Low influence implies sparse. It's very, very clear. So in some special cases, such as DNF formulas, it is known to imply conjectures in learning theory, such as the Minzer conjecture. But I think that it would be fair to say that the original motivation for Friedgut and Kalai was for the study of sharp thresholds, so in particular for graph properties. So there is also a relation there. But here I should add a remark that if you only care about functions that have lots of symmetry, such as graph properties, then there are other statements, such as the work of Fourier and Kalai, that can bypass this Fourier-Entropy conjecture and still get very good results. And actually, so I'm not sure that I will say it or that I will say it later, but this work of Fourier and Kalai is really intimately related to the work that I'm going to present today, but it's a challenge it's a challenging exercise to figure out how exactly. Good.
So Dor, maybe, I mean, it's something that would come up, I guess, again and again, but it's important to state that these results sort of take advantage or really use the fact that the function is Boolean and are not, right? They are sort of not true for functions that are just bounded.
Yeah, so this is a good point. Yeah, so these results are certainly not true for functions that are arbitrary. There is some hope that you can come up with a statement for like bounded functions that will be equivalent to the conjecture for Boolean functions, but yeah, the statement as is does not hold for bounded functions. Thank you, Avishai.
Dor, there was a question on the stream.
Okay.
It was answered. Never mind.
Okay. Yeah. Good. Yeah. So this conjecture is still wide open, and in order to make progress on it, people suggested variants of the conjecture that are weaker in the hope of getting some results. And a very interesting sibling of it is what is called the Fourier-Entropy conjecture, due to O'Donnell. And by the name, you can guess what the conjecture says. Instead of Shannon entropy, you have mean entropy. And other than that, the statement is the same. And again, the mean entropy here is the minimum of this log 1 over FS squared. So this is, again, a very interesting statement. It is weaker than the Fourier-Entropy conjecture, but stronger than the KKL theorem. So it's somewhere in the middle. But despite that, it's just as wide open. We don't know, we don't know how to prove it. Good. So what is known about this conjecture and what are the new results? So there has certainly been some work trying to attack the conjecture. And I'm not going to be exhaustive by any means. I'm just going to mention some things that I remembered off the top of my head. So the conjecture has been studied for classes of functions, such as symmetric functions, or it was proven to be true. To study it for random DNF formulas, for constant read decision trees. And also you can combine instances where the conjecture is known and get another instances where it is known. And also, if you want to get a bound with some maximum sensitivity inserted into the picture, then you can also do that. Yeah, but I think it would be fair to say that all of these results are a bit far from establishing the full power of the conjecture. And also, there have been some works about the mean entropy conjecture, So there have been some variants that were proved where we replace total influence with some other complexity measures. But again, it's a bit far from the conjecture itself. But at least for the mean entropy conjecture, you can say you can prove something that looks at least aesthetically similar to the conjecture itself. So you can prove that the mean entropy of f(h) squared is at most square of the total influence. So you may look at it and say, okay, at least we have something. But the point here is that this does not really break the logarithmic barrier, because you can think about it. This just follows from Friedgut theorem without much difficulty. So it really sort of misses the point of the entire conjecture. Good. Yeah, so what am I going to talk about? So what is our result? So here is like one corollary of our result. We prove that for all balanced Boolean functions, it holds that the mean entropy of f(h) squared is at most this total influence times log of total influence. So this gets quite close to the conjecture because you only have this log influence term to get rid of, but it's still not a conjecture. Still you get some nice corollaries. But in fact, our result is a bit stronger than that. And in a moral sense, what we can prove is that the Shannon entropy of the distribution is at most the same bound. Is at most total influence times log of total influence. Yeah, but this is moral. So there is this word morally, which no one never knows what it means. And to explain formally what I mean by that, I need to introduce a little bit more basics. Good. So we've had the Fourier expansion of a function. We've had this notion of inferences, and it makes sense to ask whether you can express inferences as some sort of functions of the Fourier coefficients. And this is indeed possible, it's not hard. So here is a lemma. If you have a Boolean function and you want to know what the inference of the ith variable is, then this is exactly the sum of squares of Fourier coefficients over characters that contain the variable I. And if you think about it, it makes a lot of sense, right? We said that this is a distribution. So this sum of characters that contain I is exactly the mass that is put on characters containing I. So it makes some sense that this will have some relation with inference, and indeed, this is the case. The proof is not hard, we'll not do it. And now I can at least explain to you why total influence is sometimes called the average degree. And this is for a very simple reason. If you take this lemma and you sum it over all I, you get that the total influence of f is equal to the summation over s of the size of s times the Fourier coefficient of s squared. And remember, this is a distribution, this squares. So this is really the expected size of a character in the Fourier expansion of f. So if this is not called average degree, then nothing will be called average degree. Right? This is the only thing that makes sense. And at this point, I want to make two remarks. These are side remarks, meaning I will say them, but then we'll forget about them for a short time. So I want to say that now that we know that the total influence is the average degree, we sort of have this image in mind that functions with low total influences are really functions that are approximated by low degree polynomials. Because if you know that the average character size is k, and you ask how much mass is there on characters more than k over epsilon, then you know that by Markov inequality, this is at most epsilon. So the functions that we study are really low degree polynomials plus some error. Of course, this is all structured and correlated, but this is really what is happening. So in particular, tools about low-degree polynomials will be useful for us. And this will be hyperconductivity, but I'm jumping a bit ahead. Okay, so I said this is side remark, so let's put it on the side and get back to stating the results. So now that we have this equivalent formula for the total influence, we can state an equivalent formulation of the Fourier-Entropy conjecture. And this equivalent formulation simply replaces the total influence with the formula that we have. Yeah, equivalent formulation. So what's the point of that? The point is only to make similarity between the formulation of the conjecture and our main result. So here a theorem. So we can prove that, again, for all Boolean functions, if you look at the Shannon entropy, then it is at most this expected character size, except that you pay some log character size in there too. So for most reasonable functions, this is the same as total influence times log total influence, but for some odd functions, it may not be the case. But still, this is, yeah.
Sorry, we have a question by Ryan. Yes, the trivial observation about influence isn't enough for the Fourier-Kalai result. Is it correct?
Yeah, because what you get from the KKL is some log n sharp threshold, but what you want for graph properties is log n squared. So this is exactly the square that you lose. Good. Yeah, so this is what separates us from proving the conjecture, this log s term, but this you can still get some things out of this theorem. Good. But actually, again, our result is a bit more general, and it's useful that we can say it. So you may wonder what happens if I look at the Shannon entropy, but up to a certain level, up to level T. And how does this relate with the total influence? So we can address this question. So you can say, so yeah, this theorem is a bit notation heavy, but basically what the message here is that if you look at this Fourier-Entropy conjecture, we can truncate both expressions at some level and roughly get that the inequality holds, except that again we have this to pay this log s term plus some total influence. But it's not such a big deal, this total influence term. So in the paper, we have some more variants and there are some other variants that do not appear in the paper, but this is really the main one. Yeah, so some implications of this theorem include, again, something in the moral sense of the Fourier-Entropy conjecture. So we can prove that if the total influence of F is at most K, then the Fourier spectrum of F is sparse, e to the K log K is sparse. So again, we miss this log K factor. As a result, we get improved performance for the low degree learning algorithm for the class of total influence function. And finally, we can even slightly improve the sharp threshold results of Fourier-Kalai. So Fourier-Kalai cannot quite prove log n squared bound for graph properties, and we get a bit closer to log n squared. Good. Yeah, so let's go back to overview. So we've gone over the basics. I told you what the Fourier-Entropy conjecture is. I stated our results. And now we're going to talk about hyperconductivity. But before that, if there are any questions, then this is a good time.
So you referred to the Fourier-Entropy, and then the easier way to remember it, which is this concentrated on 2 to the k coefficients. I see that one implies the other, but they are not completely equivalent, right?
No, they're not equivalent because even if you have some small mass on some coefficients, they may contribute arbitrarily to the entropy.
So, for example, you could say that just by Friedgut, you get like a bound of, 2 to the k squared on the number of coefficients, but you don't get any bound on the entropy, right?
Yeah.
That doesn't depend on n, right?
Yeah. That's fair to say. Yeah. Good. Okay, so let's talk about hypercontractivity, and again, we'll do it slowly. So remember the side remark that I told you earlier. So when we're dealing with low influence functions, what we're really dealing with is low degree functions with some tail after them. And this begs the question of what can we say about low degree polynomials? Because maybe if we can say something interesting about them, maybe we can translate it to some interesting observations about Boolean functions with low influence. So this is a general question. We have a multilinear polynomial P from -1, 1 to the n 2 reals with degree small, say some d. And we want to prove something for it. So what is sort of the most generic things you can ask for? Well, you can ask for concentration inequalities. So let's go to the most basic case you can ask about. The case of degree equals 1, and the polynomial is your dream polynomial. It's like 1 over square root of n times the summation of xi. So in this case, so we know how this polynomial behaves. We know that its values behave roughly like a standard Gaussian by the central limit theorem. So you have whatever you want. You have moment bounds, you have tail bounds, you have anti-concentration bounds, you have everything. So that's great. So let's make it a bit more general. So what about general degree 1 case? What about general linear polynomial P? Well, it does not have to behave like a Gaussian. You can't have it all. But other than that, you have everything that you want. You have moment bounds, you have tail bounds, and you have anti-concentration results. And for this talk, what will be important is the moment bounds. So for example, you can prove the following moment bound. I'll call it baby hyperconductivity. So this theorem says that if you have, again, this multilinear polynomial of degree 1, and you look at its fourth norm and its 2 norm, then these are roughly the same. So it is always the case that the fourth norm of P is at least the 2 norm of P. But what this baby hyperconductivity statement tells you is that up to a constant, which happens to be square root of 3, these 2 norms are the same. So this is the baby hyperconductivity. It's not too hard to prove, but actually you have something more general. But this is already called hyperconductivity, and this is due to Bonomi, Beckner, and Gross. It tells you that if now you have a multilinear polynomial of degree d, not degree 1, then you still have roughly the same statement. You still have the fourth norm of P and the 2 norm of P are roughly the same, but you pay more in the constant. So at first sight, I encourage you to think of this as a constant. So then the fourth norm of P and the 2 norm of P are the same. But if you want to be a bit more precise, then what you need to note here is that the dependency on D is exponential. Ultimately, this is what goes into this logarithmic barrier. But this is all I want to say for now. Great, so we have this hyperconductivity. And if you're anything like me, when you first see this theorem, you may say, okay, that's a nice inequality, but so what? What does it even mean? Why should I care about it? Yeah, so let me try to convince you that it is useful. Yeah, so hyperconductivity 101. So let's prove a basic fact. So suppose we have a function on the cube that gets the values -1, 0, and 1. And this function satisfies that the probability it is non-zero is exactly delta. And delta should be thought of as small. Then the degree of P is at least log 1 over delta, up to a constant. Good, so let's see the proof of this fact. And the proof is one line. You write down the hyperproductive inequality. You note that in this case, you can actually compute the fourth norm of P and the two norm of P, which are just delta to the fourth and delta to the half. Then you rearrange, you take a log, you do whatever you need, and you get the result. Okay, very, very nice. But you may say, okay, so, but no, why are you complicating life? This is just a corollary of the Schwarz-Zippel lemma, which is a fair point, right? But right, this is 101. It's not 102. But the cool thing is that actually, with roughly the same proof idea, you get a much stronger statement than this fact. So you get the following robust fact, which roughly speaking says that not only is P of high degree, but most of its mass lies on high degrees. So here is the formal statement. If you look at this function, again, probability it is non-zero is delta, which is small. And you look at the squares of the Fourier coefficients that lie on low levels, and by low I mean less than log 1 over delta, then this is small. This is at most delta to some power greater than 1, say 9 over 8. And the point I want to stress here is that if you look at the entire Fourier coefficients of P, then they sum up to delta by Parseval. And here you get that on the low levels, you have much less than delta. So this really tells you that not only is P of high degree, but it is robustly of high degree, if that statement makes any sense. Yeah, so now we'll prove this robust fact. And once we do that, we'll be halfway towards proving the Kahn-Kalai-Linial theorem. So here's the proof. So we want to argue about the low degree part of P. We want to say that there is a little mass there. So it makes sense to define this function, G, which is exactly the low degree part of P. Then the mass that we want to talk about is exactly the inner product between G and P, like by Planck-Charles. And remember, all we have in our toolbox right now is the basic hypercontractivity theorem, and that requires us to have some four norms in our proof. So let's invent some four norms. So we can bound the inner product between G and P by Holder inequality, by the product of the 4 norm of G times the 4/3 norm of P. We can then use the hypercontractive inequality to bound the 4th norm of G. And finally, you can know that the 2 norm of G is the 2 norm of P, again by Parseval. And now we're done. Now all you need to do is plug in the exact bound you have for the various norms of P, which again we can compute as before. You plug in the degree of G, and you're done. Good. Good. So I hope it wasn't like too quick, but yeah. So but this is an important fact. This is you can improve it in various ways, but this will be enough for us. Yeah. Good. So now hypercontractivity 102. How do you use this result to prove results such as the Kahn-Kalai-Linial theorem? So this is what we'll do now. I'll show you how to get the KKL theorem from this fact. So here is again the statement. We want to prove that if the total influence of f is small, then there is a variable with relatively high influence. So let's do it. And we'll do it by the way of contradiction. So let's assume that all of the influences are small. Say all of them are at most e to the minus 100k. Now we want to appeal to our robust fact. So what functions does it make sense to define that will have small probability of being non-zero? Well, we need some function that is non-zero only when you have influence. And the discrete derivatives are exactly such functions. So for each I, we define a discrete derivative of f along direction I, which is the difference between the value of f at x and the value of f when you flip the ith coordinate, and you divide it by 2 for normalization. So you can note two things very easily. So first of all, this is a -1, 1, 0 valued function. And secondly, if you want to know what the Fourier transform of this derivative is, it's very easy to see. So it's there on the slide. Good. So we'd like to use this robust fact on the discrete derivatives, and for that we need to note that the probability of derivative to be non-zero is smaller. And indeed, this is exactly equivalent to the assumption that the influence is smaller. So the probability of derivative is non-zero is exactly the same as the influence of variable I, which is at most e to the minus 100k. Therefore, by the robust fact, we know that derivatives are mostly high degree. So let's write it down. We know that the mass of the derivative that lies below level 10k is at most influence to the 9/8. And it will be convenient to break this influence to the 9/8 down into influence times influence to the 1/8 and bound the influence to the 1/8 by the bound that we have. But remember, we want to say something about the function f. So we want to express this Fourier sum of the coefficients of the derivative according to f. But again, we have the Fourier transform of derivatives, so it's very easy to do. It is exactly equal to the sum of square of the Fourier coefficients of f that contain I and are of size at most k. And now the proof is almost complete. All you do now is sum this inequality up over I, and then you get that the total mass of f below level 10k is at most this e to the minus 100k over 8 times the sum of influences. Sum of influences is the total influence is at most k. So you get that this is very small. Say it's smaller than 0.1. Now we're done, because we know that we have a total of mass 1. The mass that lies on low levels is at most 0.1. So it means that almost all of the mass lies above level 10k. So in particular, the average degree has to be at least 0.9 times this 10k, right? Because we have 0.9 of the mass above it, and this is the bare minimum that they contribute. And this is more than k. But remember, average degree is the same as total influence, which is less than k. So this is a contradiction. So this is how you prove the KKL theorem. And kind of the reason that I'm showing to you this proof is not only because it's nice, and it is nice, I think, but also is that our proof will build on it in a non-obvious way. So I thought that it would be good to see it. Yeah, so let me summarize what we've seen so far. So we've seen all of the basics, the statements, we talked about hyperconductivity. I showed you the proof of the KKL theorem. And I think that now will be a good time for a break. So after the break, if you didn't hit your Boolean analysis quota for the day, I'm going to tell you a little bit about our proofs and how to use these tools to analyze Fourier-Entropies. And yeah, so I think that this is it for now, and I want to thank you for your attention so far. So if there are any questions, now is a good time. Otherwise, let's take a break until I don't know when.
Prasad, maybe we should take a 10-minute break? That sounds good.
Yeah, we could take a 10-minute break. Should we do questions after the break, or you want to do it now?
We could do it now. I don't see any questions in the.
Okay. Yeah, let's ask again.
But yeah. Okay. Yeah. So great. So I hope to see many of you when we dive into the details of the new results. And yeah, let's take a break to get some coffee. And I'm going to pause the recording for now so you can speak.
So when are we returning, Shai?
Let's say 10 minutes from now.
So okay. 11:03.
Okay.
I guess one more thing. There is a Discord channel, which the link is posted here. One could continue discussion there.